was your cue.
My cue. Okay. So in my first lecture, I gave an outline of what I was going to do in these lectures, and I wasn't sure what I was going to do with the last one, and I'm still not sure. So let me take a vote right now.
You can cut this part out. Just start it when the lecture starts.
So one possibility is by saying something about the Mumford conjecture. So let sigma be a Riemann surface of genus G. So you can look at the group of diffeomorphisms of sigma, and here I'm always going to mean orientation-preserving diffeomorphisms. And this has a classifying space, B diff sigma. And this classifying space you can think of as a classifying space for surfaces of genus G. In particular, there's a universal surface of genus G which lives over sigma. Namely, if you take a contractible space E diff sigma on which diff sigma acts freely, cross it with sigma, and mod out by the action of diff sigma. So this is a fiber bundle whose fibers are copies of sigma. So people are very interested in these sorts of objects, for example, in algebraic geometry. And one thing that you might want to do is, say, study the cohomology of one of these classifying spaces. So there's a natural way that you can start writing down some cohomology classes, namely, let's have a name for this. Let's call this E. It's the total space of a fibration. So on E, there is a canonical two-dimensional vector bundle V, which is just given by taking the tangent bundle to the fibers of these maps. So this is a two-dimensional vector bundle, therefore it has an Euler class. The Euler class of V, which lives in H2 of this space E with coefficients in, let's say, the complex numbers, or let's say the rational numbers. And then you can look at its powers. E of V to the power k plus 1, or let's say n plus 1. This lives in H2n plus 2 of E with coefficients in Q. Well, these are classes in the cohomology of E, but now E is a surface bundle over B diff sigma. So if you have a cohomology class on E, you can integrate it over the fibers of this map to get a cohomology class on the base. So by integration, you get classes, and I think I'm going to use, I think I have the notation right, kappa n in H2n of this classifying space B diff sigma with coefficients in Q. Now we have these classes for every n, and that we can use them to make other classes by adding them and multiplying them. So these classes give us a map from some big polynomial ring, Q adjoin variables, kappa 1, kappa 2, and so on, into the cohomology of this space B diff sigma, coefficients in Q. So the Mumford conjecture is the statement that this is essentially accounting for all of the cohomology. More precisely, this accounts for all of the cohomology in some limit as we increase the genus of sigma more and more. So the Mumford conjecture says that this map, it's a map of graded rings where each kappa I has degree 2i, and over here you have the usual grading on cohomology. The Mumford conjecture is that this map is an isomorphism in a range of degrees which goes to infinity as G goes to infinity. So this was Mumford conjecture was proven by Madsen and Weiss, and that proof has subsequently been embellished a little bit, or parts of that proof have been embellished by Galasius, Madsen, Tillman, and Weiss. And I'd like to explain that embellishment because it's closely related to the things that I've been talking about in this lecture series. Part of the proof can be regarded as a special case of the Cobordism hypothesis. So let me sort of outline how you go about, or what some of the steps are in proving the Mumford conjecture. So first, why might you believe that this has something to do with topological field theories? So let's recall in these lectures we have been studying an infinity 2 category which I denoted by board 2. So an infinity 2 category is something that you can think of as like an ordinary 2 category, but where the morphisms, instead of forming sets, form topological spaces. So in particular, these classifying spaces for surface bundles appear inside of board 2. So if I look at B diff sigma, this is the classifying space for connected surfaces of genus G. And therefore, it's just a connected component of a classifying space for all closed surfaces. And a classifying space for all closed surfaces, that's precisely one of these spaces of 2 morphisms that appears in board 2. That is, if I look in board 2, if I look at Homs from the empty set to the empty set inside the infinity 1 category that I get by looking at Homs from the empty set to the empty set inside of board 2. The empty set here means the empty 0 manifold. Homs from the empty set to itself are 1 manifolds, and there's an infinity 1 category of them here. Particular examples of objects of that infinity 1 category are the empty 1 manifolds, and Homs between the empty 1 manifold and itself in this context are Cobordisms from the empty set to itself. Those are closed 2 manifolds. So that's what this is saying. So the upshot of this is that this classifying space is somehow related to this object board 2. Now, this here just means a topological space, whereas board 2 is a more exotic object. It's an infinity 2 category. So if I want to describe the relationship in more concrete terms, one thing I might try to do is extract from board 2 something that's something of a more concrete nature. So let me explain that. So in general, if C is an infinity n category, you can extract from C a topological space, which I'm going to write as C with bars around it. This is sometimes called the classifying space of C. And how should you think about it in the language of higher category theory? What you're supposed to do is you invert all morphisms. Just take your higher category C. It has lots of morphisms at lots of levels, and a lot of them are probably not invertible, but you could just freely adjoin inverses to those non-invertible morphisms and arrive at something where all of your morphisms are invertible. So that's an infinity groupoid. And as I explained last week, an infinity groupoid is something that you should really think of as a topological space. And that's what's called the classifying space of C. And just as an aside, is that if you were to use the model that I described last Thursday for higher category theory, I described the complete Siegel space model for infinity 1 categories, where an infinity 1 category was just defined as a simplicial topological space. And that generalizes to higher n, where you think about n-fold simplicial topological spaces. So if you think about C in this way, as an n-fold simplicial space, then this classifying space is given by forming the geometric realization. That is, there's an explicit recipe, namely, if you think of this as a simplicial space, so you have topological spaces C sub n for every n, then what you're supposed to do is take all of these C sub n's, cross them with the interval, and glue them together in some way, using the structure of C as a simplicial space, modulo gluing. Okay, so so how can we think about what's going on here? Well, this classifying space for closed surfaces maps into this Hom space here. And now this Hom space, let's say, maps into the twofold loop space of the geometric realization of board 2. How are you supposed to think about that? Well, every point here gives you a 2 morphism in board 2. And that, in particular, gives you a 2 morphism in this classifying space of board 2. If you think about this thing as an infinity groupoid. And a 2 morphism in that classifying space is equivalent to giving a 0 morphism, or just a point, inside its twofold loop space. So you have a map of topological spaces from here to here. So now, the Mumford conjecture, you can split the proof of it into 3 parts. So to prove the Mumford conjecture, proof can take place in 3 steps. So first, let's call this map something. Well, first I should point something out, because I don't want to lie to you. So we have a map of topological spaces here. The left-hand side, this space B diff, that's a connected space. The right-hand side is actually not connected. So this actually only lands in one component of this twofold loop space, and that which component it lands in actually depends on the choice, depends on what genus the surface has. So actually let YG be the connected, be the appropriate connected component of this twofold loop space, so that this factors through Y sub G. So now if you want to prove the Mumford conjecture, here's what you want to do, or here's one thing that you can, one way you might go about it. So step 1 is to prove that the map from the pullback map from the cohomology of the space YG into the cohomology of the space B diff sigma is an isomorphism in a range of degrees that approaches infinity as G approaches infinity. That reduces you to studying not these topological spaces B diff sigma, but instead these topological spaces YG. And these topological spaces YG, these are just connected components of this space omega squared board of the classifying space board 2. So step 2 would be to understand that classifying space of board 2. So step 2 is, let me put that in quotation marks, understand the classifying space of board 2. And what that means is construct a homotopy equivalence of board 2 with something else. Of course, if I don't tell you what that something else is, there's no content here. But the point is, when you carrying out this step means you construct something else which really lives in the world of algebraic topology, something else which already has a name, and something that doesn't a priori have to do with Cobordism theory. And you construct a homotopy equivalence of board 2 with that. And then finally, well, so what that'll tell you that what you need to do in order to understand what the cohomology of B diff sigma looks like in a range of degrees is understand the cohomology of the twofold loop space of X. So step 3 is to compute that cohomology. To compute H star of loops 2 X and show that it, roughly speaking, looks like a polynomial ring on many variables. And I'm lying here because this is actually just the cohomology of one particular connected component. There are other connected components too. So let me just say something about all 3 of these steps. So step 1 is probably the hardest step, and I'm not going to say anything about it today. So this is the step where things like the Harrer stability theorem come into the game. Harrer stability is what tells you that you might actually expect these cohomology groups to stabilize to anything at all. Why do you expect the cohomology of B diff sigma to look like the cohomology of B diff sigma prime if sigma and sigma prime have different genus? So step 1 is what's involved. Step 1 involves this sort of Harrer stability arguments, and it's probably the hardest part. So step 2, this is a special case of a theorem which is true for all n. For all n, meaning here I've said something about board 2. There's an analogous assertion for any board n, and it can be proven. It's a special case of the Cobordism hypothesis. So that's what I'm going to explain today. And now step 3, this is a calculation. And of course you can't do this calculation without knowing what x is, but when we do step 2, I'll tell you, at least in rough terms, what x is. And then if you're an algebraic topologist, this is actually a fairly easy thing to do. Once you've put x into the world of algebraic topology, well, in algebraic topology, computing the rational cohomology of anything is supposed to be easy. But and if you're more hardcore in your ability to compute things, I think people can actually compute the cohomology of this with not rational coefficients, like coefficients mod 2 and so forth. That's a little harder. But I'm not going to say anything about that today either. So our goal is to understand step 2. And the way that we're going to do it is is using the Cobordism hypothesis. So what does the Cobordism hypothesis say? I want to spell out what the Cobordism hypothesis is saying in a special case. So let me just review the Cobordism hypothesis. Cobordism hypothesis tells me that if C is an infinity n, symmetric monoidal infinity n category with duals, then giving a topological field theory with values in C is equivalent to that first of all, if I look at the collection of objects of C, or more precisely, the infinity groupoid of objects of C, the classifying space for objects of C, that's acted on by the orthogonal group O of n. And second of all, giving a topological field theory which is valued for all oriented manifolds is equivalent to giving an SON fixed point for the action of a fixed point for the action of SON on that space of objects of C. So let's specialize to the case where C is an infinity groupoid and see what this is saying. Just remember, an infinity groupoid is just a topological space. So when we're working in the setting of topological spaces, we ought to be able to translate the Cobordism hypothesis into a statement in algebraic topology. So what can we say about C? So C is an infinity groupoid. So by what I told you last time, I can think of it as a topological space X, or in other words, it's the fundamental infinity groupoid of some topological space which I'll call X. But now C was not just any infinity groupoid. C was supposed to be a symmetric monoidal category. So we have a symmetric monoidal structure. On C, that means that I have a way of tensoring objects of C. And that process of tensoring things is commutative and associative up to coherent isomorphism. And as I think I mentioned last time, this translates into topology as saying that X is an E infinity space. Oh, wait, I said that last time, but last time was a smaller audience. So let me say a few words about this. The notion of an E infinity space, the letter E is supposed to stand for everything. An E infinity space is supposed to be a space which is equipped with some sort of a multiplication law which is commutative and associative up to homotopy and all higher homotopies, everything that you could conceivably write down. In other words, i.e., it has a commutative multiplication. But now, C was not just any symmetric monoidal category with symmetric monoidal infinity category. It's a symmetric monoidal infinity category which has duals. So what does that mean in this case? Well, as I mentioned last time, having duals means, first of all, having adjoints. That's really no condition here because all of the morphisms in the category C are invertible. So every invertible morphism always has left and right adjoints, namely given by the inverse of that morphism. So the requirement that C have adjoints doesn't tell us anything if we know that C is an infinity groupoid. The requirement that C has duals tells us a little bit more, though. It tells us every object of C has a dual. Well, isomorphism classes of objects of C can be thought of as elements in pi naught of the space X. This requirement that C has duals tells us that pi naught of X is actually an abelian group, where its group structure is given by this E infinity structure, this commutative multiplication that we have on X. So both of these things together, plus some algebraic topology, tell us that X is an infinite loop space. i.e., for all n, there exists spaces xn, pointed spaces xn, such that x is homotopy equivalent to the nth loop space of xn. So if you're not comfortable with this fact of algebraic topology, you can feel free to ignore it in what I'm about to say. I'm going to talk about infinite loop spaces, and infinite loop spaces is going to be shorthand for spaces with this structure. So if C is an infinity groupoid, which is a symmetric monoidal infinity n category with duals, that means I have an infinite loop space. Now what is the Cobordism hypothesis telling me? Well, first of all, if C is an infinity groupoid, then tensor functors from board n into C are the same thing as tensor functors from the classifying space of board n into C. Because the classifying space, remember, this is the infinity groupoid that you get by inverting all of the morphisms in board n. Now, all of the morphisms in C are already invertible, so if I just want to compute functors into C, there's no harm in throwing in inverses. And now, both the left-hand side and the right-hand side are symmetric monoidal infinity groupoids with duals. In other words, they fit into the world of infinite loop spaces. So this is equivalent to the space of maps in the world of infinite loop spaces from this classifying space board n into this topological space X that I was studying on that other board. All right, so this is something that we could try and compute. Well, we have a similar picture if we use the framed Cobordism category. Tensor functors from the framed Cobordism category are equivalent to maps. Let me write IL for infinite loop maps from geometric realization of this framed Cobordism category into X. But the Cobordism hypothesis will also compute this for us. The Cobordism hypothesis will tell us that this is equivalent to the underlying infinity groupoid of C, which is just the space, which is just C itself, or in other words, the space X. So here's the Cobordism hypothesis being applied. And now what is this telling me? This is telling me a universal property of this classifying space. It's telling me this classifying space is free as an infinite loop space. It's freely generated by a single point. So i.e., this is free on one point. And that actually tells you what it is as an infinite loop space. It's homotopy equivalent to the stable sphere. What in algebraic topology you write as QS naught, which is the direct limit over n of the nth loop space of the n sphere. This is how you would build something if you, well, this is the natural way that you would build a free infinite loop space on one generator. It has to be an nth loop space for every n, and the fact that you have this one generator corresponds to the fact that you should take loops n on the n sphere. Okay, so that tells us what the classifying space of the framed Cobordism category looks like. What about the classifying space of this Cobordism category itself? Well, that's also computed by the Cobordism hypothesis. What does the Cobordism hypothesis tell me in that case? It tells me that this can be identified with not arbitrary points of the space X, but points of X which are homotopy fixed points with respect to the action of SON. Well, another way of saying that is that if we combine these facts, I could also describe that as the homotopy fixed points for the SON action on tensor functors from, or on the space of maps from the geometric realization of the framed Cobordism category into X. So if I compose all of these equalities, it's telling me something about it's telling me something that I can state without mentioning X. It's telling me that the geometric, or the group, the classifying space of Bord N is related to the classifying space of Bord N framed in some way that has to do with the action of this special orthogonal group. So what is this? This tells us that, in fact, this classifying space of Bord N is what I obtain from the classifying space of Bord N framed by taking the quotient, or the co-invariance, by the action of the group SON. So this is, maybe I'll write it like this, but here I'm taking the quotient in the world of infinite loop spaces. And now we know what the classifying space of Bord N framed is. That's just this free gadget, the thing I called QS naught. So you're supposed to take QS naught, and that's somehow acted on by SON, and then you're supposed to take the co-invariance for that action. So now, this is one of those actions that I told you about in the earlier this week. I told you there's an action of SON on the space of fully dualizable objects of any infinity n category. It's in general maybe hard to think about, but there are a few cases in which you can understand it in more classical terms. One of those cases is when your category is actually an infinity groupoid. Then you're really dealing with an infinite loop space, and this action of the orthogonal group comes via the J homomorphism. So this action is via the J homomorphism. And now we're really completely in the world of algebraic topology. This object has a name. This is what nowadays is denoted loops infinity minus n of MTSON. So, of course, if you've not seen this notation before, this doesn't mean anything to you. This is just a name for what you get if you do this construction. If you take here the stable sphere, and then you let SON act via the J homomorphism and take co-invariance, well, you get something, and that something gets the name of MTSON. Okay, so now we're in good shape. So if we take n is equal to 2, this is telling us something about the space that we wanted to know about. Loops 2 of Bord 2, that's just loops infinity of MTSO2. So here I'm using some notation which maybe you're not familiar with. This is this object in algebraic topology is what's called a spectrum.
Infinity or infinity minus 2? I don't know what infinity minus 2 is.
Well,
maybe that. Oh, okay.
yeah. So I mentioned that if you have a group like E infinity space, that it's an infinite loop space. In other words, there's a sequence of spaces, x0, x1, x2, and so on, which are equipped with homotopy equivalences. Each one is the loop space of the next. So a sequence of such spaces is called a spectrum. And you're supposed to imagine a spectrum is sort of like some stabilized version of a space. And a spectrum is something that you can loop infinite. It's like the limit of these xn's as n goes to infinity. And then if you wanted to get x0 from that, you would loop it infinitely many times. So a spectrum means this. Loops infinity of the spectrum means this. Loops infinity minus 2 of the spectrum means this. So MTSO2 is notation for a certain spectrum. And the thing that you want to compute for the Mumford conjecture, or the relevant space, loops 2 of this classifying space, board 2, is actually the 0th space of this spectrum MTSO2. So what we've proven is the following theorem of Galatius, Madsen, Tillman, and Weiss, which is that the geometric realization of board n in general is, well, I stated it over there, loops infinity minus n of MTSON. The point being, there's actually, these maneuvers take place inside the world of algebraic topology, and there's a very topological ways that you can understand them as taking some kind of classifying space for the group SON, looking at a certain vector bundle on it, and making a Tom space. So having said that, you've given yourself, having said that, and if you are familiar with some methods in algebraic topology, you're well equipped to compute the cohomology of this space now. It's an exercise for people who, your graduate students in algebraic topology. Okay, so that is all I want to say about the Mumford conjecture, I think. But, well, maybe I should mention, so more generally, so this theorem is equivalent to the Cobordism hypothesis. Or to the special case of the Cobordism hypothesis where the target C is an infinity groupoid. That's what this whole argument is supposed to show. So if you believe the Cobordism hypothesis, you get a proof of this theorem of Galatius, Madsen, Tillman, Weiss. And originally, the original argument for the Cobordism hypothesis actually used this as one of its inputs. So I'm not sure if the proof at present is going to need that. You might actually get a new proof of this theorem out of the Cobordism hypothesis. You might not. All right, so now I have, I don't know, 20 minutes left. Why don't let's do some other things, spell this out in some more detail, the Cobordism hypothesis out in some more detail when n is equal to 2. So actually, here's what I would like to say. So let me start by making, we'll get to the case n equals 2 in just a minute. But let me make a few remarks about the proof of the Cobordism hypothesis. So remark 1 is that it uses induction on n. Actually, that's the only remark I'm going to make, but I'm going to elaborate on this remark. So how might we try and understand this using induction on n? So let's say we have our target category C. C is a symmetric monoidal infinity n category. And we want to understand functors from board n into C. That's our goal. Well, those might be hard to understand, but our inductive hypothesis will tell us we understand functors from board n minus 1 into C. And board n minus 1 we can think of as sitting inside of board n. The phrase sitting inside is maybe a little bit misleading. It at least admits a functor to board n. So supposing we've proven the Cobordism hypothesis in dimension n minus 1, what we'll know is that we'll understand what it means to give a functor here. This is giving a functor like this is giving an object of C, object C in C, object X in C, which is an SO n minus 1 fixed point for some action of O of n minus 1 on the objects of C. And what you need to come to grips with is what it takes to extend your functor from the n minus 1 dimensional Bordism category to the n dimensional Bordism category. And the answer is you actually don't have to supply very much data in order to extend this functor. So let's say we have our functor z0. We want a functor z. So what do we need to get from z0 to z? That's a question. And the answer is you need to supply one piece of information, essentially, which is what does z do on an n-dimensional disk? What does z do on the simplest example of something which you can do in board n, which you can't do in board n minus 1? So the disk, you can regard as a Bordism from Sn minus 1, which is an n minus 1 manifold, into the empty set, which is an n minus 1 manifold. So that Bordism is an n-morphism in board n, which doesn't come from anything in board n minus 1, but the source and the target do live in board n minus 1. So you can think about this as a map from z0 evaluated on the n minus 1 sphere to z0 of the empty set, which is some sort of unit object. So this is, maybe I should say, this is going to be an n-morphism. From this thing to this thing in the category C. You need to supply this n-morphism, and it needs to be supplied in an SON equivariant way. Because part of having these field theories in a fancy sense means that z0 is actually respects the action of diffeomorphism groups. The value of z0 on an n minus 1 sphere carries an action of the diffeomorphism group of the n minus 1 sphere. And in particular, it carries an action of the rotation group SON. So there's an action of SON here. We can let SON act trivially on this unit object. And now it makes sense to demand that an n-morphism not just be any old n-morphism, but that it be equivariant with respect to the actions of these groups. So the answer is that you need to supply an SON equivariant n-morphism from here to here, satisfying a non-degeneracy condition. I would prefer not to make this non-degeneracy condition explicit. So what I'm giving you here is what you can regard as an alternative version of the Cobordism hypothesis. Rather than understanding a functor out of board n all at once, you can break it down into stages and understand what sort of data you need to supply to go from n-1 dimensional field theories to n-dimensional field theories. The answer is, assuming that C has all kinds of duals, you just need to supply these single pieces of information, equivariant with respect to SON in this case, or more generally, whatever the relevant structure group is. So in practice, the proof of the Cobordism hypothesis that I know goes through this statement. What you actually prove is this, and then you chain this together n times to arrive at understanding of what it takes to build a functor out of board n directly. Okay, so that's all I want to say about the proof. I just wanted to single this out because it's particularly useful in the case n is equal to 2. So, an example, suppose that n is equal to 2, then giving a functor z from board 2 into some target category C is equivalent to giving, well, first we need to give its restriction to board 1 into C. But now, so my notation is that board n denotes the oriented Cobordism category. But as I mentioned before, in dimension 1, there's no difference between the oriented Cobordism category and the framed Cobordism category. So this is the framed Cobordism 1 category. And therefore, the Cobordism hypothesis tells us what it takes to make a functor there. We don't have to think about any equivariance conditions. This is just an object of C. So this is the first piece of data that we need. The second piece of data that we need is what we're going to do on a two-dimensional disk. So what we do on a two-dimensional disk, this is going to be a map from Z0 of the circle into the unit. Well, something I'll call eta, or why don't I say it this way? Eta is going to be an element in Homs from Z0 of a circle into the unit.
Jacob,
Yes.
I must have gotten lost a while ago. When we were proceeding inductively, and we'd proven the Cobordism hypothesis for board n-1, C was an infinity n-1 category with duals. Okay. What do I do about the n-morphisms that aren't invariable? I mean, there's
Well, you could.
Okay.
So giving a functor from board n-1 into C is equivalent to giving a functor from board n-1 into the n-1 category that I get by discarding the non-invertible morphisms.
I see. Okay.
And if it had duals in the n sense, that's stronger than having duals in the n-1 sense. So
I see. Oh, that's the part that I was missing. Okay. Okay.
So you have to supply a map from Z0 of the circle into the unit, and that map should be invariant under SO2, or in other words, invariant under the action of the circle group. Such that, and furthermore, it should satisfy such that eta is non-degenerate. So now, this is something fairly concrete that we could apply if we had some infinity 2 categories around. So let me try and give some examples. How much time have I got? A little bit. What's that?
In principle, half.
In principle, half an hour. But, well, I'll talk for a little longer, and then I'll open for questions or something. I don't know. So if you want to apply the Cobordism hypothesis, the first thing that you have to do is choose an appropriate target category. So the statement that I just made, I was assuming that the target category had duals. Let me not make that assumption now. In that case, I should say that this object x in C is fully dualizable in order to apply this hypothesis. But as Jacques points out, what I really mean, it's fully dualizable in the category that I get by discarding the non-invertible two morphisms in C. In other words, being fully dualizable in an infinity 1 category just means having a dual. So this is just a dualizable object, X in C. And then the condition of being fully dualizable in the 2 sense actually gets absorbed into what non-degenerate means here. Okay, so let's try doing an example. So I gave some examples of topological field theories on last Thursday. And one of them was the B model associated to a Calabi-Yau variety. So let me try and give this example here now again. So let C be an infinity 2 category, defined as follows. So the objects of C are going to be algebraic varieties over the complex numbers. Morphisms from X to Y in C are going to be chain complexes of quasi-coherent sheaves on X cross Y. And now, when I give a description like this, I'm obligated to tell you how you're going to compose morphisms. So what is your composition? Let's say you have a chain complex on X cross Y, a chain complex on X, Y cross Z, and what you're trying to make is a chain complex on X cross Z. And what you're supposed to do is write the following diagram, where up here I have X cross Y cross Z. Take your chain complex here, pull it back to X cross Y cross Z. Take your chain complex here and pull it back, and tensor them together, and then push forward along this map here. So composition is given by, what should I say, push-pull using this diagram. And now it's implicit when I'm saying this that really I don't mean take all of those constructions literally. We're doing homological algebra here, so you really need to perform the derived functors everywhere. You should really, before you pull anything back or tensor anything together, you should make sure that you choose an appropriate free resolution, and before you push anything forward, you should choose an appropriate injective resolution. So let's say two morphisms are given by maps of chain complexes. And again, this needs to be appropriately derived in the sense that given two chain complexes, you don't necessarily expect that you have enough maps between them until you've performed an appropriate resolution. And now we also have higher morphisms given by chain homotopies. Chain homotopies between chain homotopies. And so on and so forth. So this is, of course, only a sketch of a definition of an infinity 2 category. This is an idea that you might try to implement. And one of the reasons that for introducing an elaborate formalism like the formalism of Siegel categories last week is that all of these issues about performing the appropriate resolutions before you apply any of these constructions, those issues are a lot easier to deal with in a fancier formalism than they are in something simpler where you think about simplicial categories or topological categories. Okay, so here's an example of a two-category that we might try and find a fully dualizable object in. So what do we need to do? Or we might try and find a full-oriented field theory here. We might try and find all this data. What do we need to do? Well, so goal, let's find a dualizable object first. This turns out to be really easy. It turns out every object is dualizable. In fact, every object is its own dual. Every object in C is self-dual. What do we need to check to check this? So I'm claiming that, maybe I should have mentioned, this is a symmetric monoidal. The symmetric monoidal structure is given by taking products of algebraic varieties. So every object of C is self-dual in this world. So what do we have to check that? Well, we need candidates for a co-evaluation map and an evaluation map that go from the unit to x cross x and from x cross x into the unit. So the unit here, the symmetric monoidal structure is given by products. So the unit is just the unit for products, which is the algebraic variety consisting of a single point. And now what does it mean to give a morphism from a point to x cross x in this two category? Well, it means that we have to give a quasi-coherent chain complex of quasi-coherent sheaves on a point cross x cross x. So there's a natural candidate for what that is, namely take this co-evaluation map to be the structure sheaf of the diagonal embedded in x cross x. In other words, the push forward of the structure sheaf of x along the diagonal. And you can take the evaluation map also to be the same thing. The structure sheaf of the diagonal. And now I'll leave as an exercise for you to contemplate that this evaluation and this co-evaluation are compatible with one another if you were to perform these constructions, if you were to compose them in the appropriate ways and derive all of the constructions appropriately, you would get you would see the compatibility that you wanted to see that said that those things were giving us a duality of x with itself. Well, now I've erased the other kind of data that I want to supply in order to get a two-dimensional field theory. So let me remark, this is already enough to get a one-dimensional field theory. It assigns to a point the algebraic variety x, and it assigns the only other interesting thing we could ask about is what it assigns to the circle. So given x, that gives us a field theory from the one-dimensional Cobordism category into C. And now what is Z naught of a circle? Well, this is something that we computed in the first of these lectures. It's what you might call the dimension of x. It's what you get by composing the evaluation map, which goes from x cross x to a point, with the co-evaluation map, which goes from a point to x cross x. So I've told you what this evaluation and co-evaluation map are supposed to be. And now I have to tell you what is the composition in this world. I've told you how to compose things, and now we just have to see what we're going to get when we do that. So the diagram that we want to contemplate, here's x cross x, here's a point, here's a point. This co-evaluation map you should think of as being given by this correspondence. X maps diagonally into x cross x, and it also maps to a point by the projection. And similarly, this evaluation map is given by this correspondence. And now what you're supposed to do is compose these correspondences. In other words, you're supposed to, if we follow this prescription here, what we're supposed to do is take OX, the structure sheaf of the diagonal, and tensor it with itself inside quasi-coherent sheaves on x cross x. And then what we get is a quasi-coherent sheaf on x cross x, and then we're supposed to push it forward to a point, and we get some complex of quasi-coherent sheaves on a point. In other words, a complex of vector spaces. So this is a complex of vector spaces over C, where pi is the projection from x cross x to a point. But remember, as I mentioned, we really need to derive all of these constructions for this to be sensible. So this needs to be a left-derived tensor product, and this needs to be a right-derived push forward. So when I discussed the B model originally, I told you that there was some way of globalizing the construction of the Hochschild homology of an algebra. And in fact, this is it. This is the definition. By definition, this is the Hochschild homology of the algebraic variety X. So in fact, this field theory formalism is producing, in this example, an interesting invariant of a variety X, namely its Hochschild homology, if I plug in the manifold, which is a circle. So now, to get a two-dimensional field theory, we need more. We need this thing that I called eta, which is supposed to live inside maps from Z naught of a circle into the unit, and it should be a fixed point with respect to the action of the circle group. So what are all of these things? Well, first of all, where is this Hom taking place? This is a space. This thing here is supposed to indicate a space of two morphisms in the category C. Namely, two morphisms that go from the identity of the empty set to itself. And so the relevant category that we're taking Homs in is something I've already mentioned. It's really sort of Hom. It's the category of Homs from a point to a point in C. A Hom from a point to a point in C is a complex of quasi-coherent sheaves on a point. In other words, a complex of vector spaces. So this I should really think of as Homs in the world of chain complexes. And now what is Z naught of a circle? That's what we just computed. That's the Hochschild homology of the variety X. And now what is the unit object? Well, that's just the complex numbers. And what's the upshot? We're looking for some kind of a trace defined on Hochschild homology, taking values in the complex numbers, and it should be, in some sense, circle invariant. Another way of saying that is, this is Homs of chain complexes. I could replace the Hochschild homology by circle co-invariance on Hochschild homology to get what's called the cyclic homology of X, with values in the complex numbers. Well, this is something that we're not going to get for any algebraic variety X. It's something that you only expect for a Calabi-Yau variety. So if X is Calabi-Yau, and then in fact, if I look at the Hochschild homology of X in degree minus Calabi-Yau of degree of dimension n, and I look at the Hochschild homology of X in degree for any x, if I look at the Hochschild homology of X in degree minus n, then what I'm going to get is, I'm about to say something false, aren't I? No. Hochschild homology of X in degree minus n is h naught of X with coefficients in the dual of the canonical bundle of X. Somebody check me, make sure I'm saying this, not saying this backwards. But now if X is Calabi-Yau, this can be identified with h naught of X with coefficients in OX. So if X is, say, compact, that's just the complex numbers.
Just the canonical rather than dual?
What's that?
Maybe canonical rather than dual?
Well, you know, I really want to be doing this in degree. Give me 1 second.
Partial complex is differential forms.
This is, sorry, minus n. This is what I want to write, right? That's what I want to write. Hn of X with coefficients in OX. So I'm saying it in a way that I want to trace out rather than an element of. That's what was throwing me off. So this is, if X is Calabi-Yau, that's the same thing as Hn of X with coefficients in its canonical bundle. And then you have some canonical trace map to the complex numbers.
So that's not an isomorphism, but a map? There's a map from log minus n to Hn?
That's an isomorphism, isn't it?
Isn't it a direct sum of Hp of X with...
I mean, the Hochschild homology is going to live in degrees n through minus n. I'm looking at what's at the very bottom. Right, because this tensor construction lands in homological degrees, and this push forward lands in cohomological degrees. You can say what happens at the very top and the very bottom. Anyway, I may have said something slightly inaccurate, but the gist of it is correct. If you have a Calabi-Yau variety, there is a canonical trace that you can write down, although it doesn't quite fit into this framework. I'm lying to you a little bit because this is actually a map not of degree 0, but a map of degree n. So just disclaimer, the following is all lies unless you introduce an appropriate twisting. So I'm going to ignore the fact that this is landing in the wrong degree. If you didn't want to ignore it, you would have to start with a fancier category to begin with than the one that I told you about. But ignore the fact that this is in the wrong degree. This is indeed a map from the Hochschild complex of X into the complex numbers. And just for degree reasons, any such map will automatically be circle invariant. So here we get eta if X is Calabi-Yau. And now what does it take to make a two-dimensional field theory? Well, I never quite told you, and I've erased it anyway. But remember that we needed to say what our field theory did on a point. We needed to say what it did on a disk in a circle equivariant way. and we needed to check some non-degeneracy conditions. So we get eta if x is Calabi-Yau, and now the non-degeneracy of eta in this case comes down to the Serre duality. That is, this trace map on Hn of x with coefficients in its canonical bundle is supposed to give you some sort of perfect pairing between cohomology of x with any coefficients and the cohomology of x with coefficients in coefficients of x with coefficients in E, tensored with the coefficients of x, cohomology of x with coefficients in E dual tensor omega x. Using this trace map, there's some sort of pairing. This pairing is perfect. That's what Serre duality tells you. And if you unwind the kind of non-degeneracy conditions that you need to contemplate here, at least some of them amount to the requirement that Serre duality be satisfied. So the upshot is we get a two-dimensional field theory. Associated to x and it is what some people call the B model. In particular, we get what I told you about last Thursday, namely we get an ordinary topological quantum field theory valued in Z2 graded vector spaces, which associates to a circle not the Hochschild chain complex of x, but the actual Hochschild homology of x, and which associates to surfaces of higher genus some sort of operations on the Hochschild homology. Okay, so I think I will stop there and take some questions.
Questions?
So suppose I have two closed manifolds that admit good covers that have the same combinatorial structure. Will TQFTs in this sense return the same value?
I don't see that they necessarily would. But, well, I don't think I have anything useful to say about that.
So say we supplied the extra piece of data, namely Z of a disk.
Mm-hmm.
Right? What happens if we took the B model and tried to go up to n equals 3? What do we get? I mean, we have to supply that piece of data, but is there some candidate for that that gives some interesting three-dimensional TQFT?
What's the target category in that case?
Keep the target category the same as before.
But then there are no non-invertible 3 morphisms. So
I see. Okay, so that's part of the. I see.
Could you say something about how the non-degeneracy of this trace on the disk relates to existence of adjoints?
yeah. Yeah, so let me tell you a little bit about what it means to be non-degenerate. So I was telling you a little lie here when I say the non-degeneracy of eta is equivalent to Serre duality. It's more like Serre duality is half of what you need to check for the non-degeneracy of eta. So, so let me say what that non-degeneracy condition is. Let's look in pictures. So what are the relevant pictures in the Cobordism category? So we have an object which is a point. And now here's x cross a tensor x dual. It's 2 points, maybe with opposite orientations. Let's not worry about the orientations. And now here's the co-evaluation map, and here's the evaluation map. And now what is the disk? Well, the way I said it, it's a map from S1 to the empty set. And S1 is the evaluation composed with the co-evaluation. It's what you get when you glue these two circles together. So this, on the other hand, what is the empty set? This is the identity map. Well, on the empty set. This is the empty set as a 1 manifold. Here I mean the empty set as a 0 manifold. So what is the 2 disk? It's a map from a composition of 2 1-morphisms into the identity of the empty set. Now we're in the context that I was describing last time. We can ask whether or not this is the unit of an adjunction, or the co-unit of an adjunction. So here we have a map. Now we could ask the following question. Is eta the co-unit of an adjunction? Now asking whether something is the co-unit of an adjunction, it's like asking whether or not a well, let me not say that. So so now you might object to my assertion I made earlier. Earlier I said that in order to define an n-dimensional field theory, you start with the n-1 dimensional field theory, then you say what you did on the disk, and that determines everything else. And that sounds an awful lot like I'm saying any n-manifold you can get by gluing together disks. But in general, if you tried to build an n-manifold, the way you might try and build it is by taking some sort of a handle decomposition. And sort of disks glued along their entire boundary are only giving you handles of index 0. Where do the other handles come from? And the answer is that the other handles are hidden in these non-degeneracy conditions, which I didn't make explicit. So the non-degeneracy condition, the first non-degeneracy condition that eta has to satisfy is that, so non-degeneracy implies that the answer is yes. Here's the first requirement that you need to make of this map eta. So now let's see what that would buy you. If you knew that eta was the co-unit of a junction, what would you know? So if eta is a co-unit, then there exists a compatible unit. Let's call it eta prime. So where does eta prime go? It maps into the co-evaluation composed with the evaluation, and the source is the identity, but now not the identity on the empty set, but the identity on this object, the identity on 2 points. So the identity on 2 points, that's the Cobordism that you can draw like that, and co-evaluation composed with evaluation, that's not a circle, that's this picture. So now what is this map eta prime? What is the Cobordism that you want to draw? Well, let me draw it this way. It's a saddle. And so why is the saddle the right thing to draw? Well, the claim is that the saddle is a compatible unit for an adjunction with this thing as co-unit. There's some compatibility between the disk and the saddle, which, when you translate it into geometry, is the following. It says that if you take a saddle that looks like this, and you imagine taking a half cylinder, laying it next to the saddle here, and then capping off with a disk, the result, you have something with a hump here. You could imagine pushing the hump down, and you just get a half cylinder. That's one of the compatibility between the unit and the co-unit. The other compatibility is the same thing on the other side. So maybe I should, more generally, the compatibility here between eta and eta prime amounts to some sort of handle cancellation. So just assuming that eta is the co-unit of a junction forces there to be a compatible unit, and that compatible unit is supposed to correspond to what our field theory is going to do on a handle of index 1. Now, of course, handles of index 0 and handles of index 1 are still not enough. We need handles of index 2. Well, there's a further non-degeneracy condition on eta, which puts handles of index 2 into the game. But it's a little more complicated to state, so let me not say any more.
Okay, well, let's thank Jacob again for a great lecture.